Day 24. We've got about 30 people-ish who have completed every day so far. That is all days up to 23. If we look at the top three, we've got Daniel in first, a new first place. We've got Taklim coming in at second, and Sergey coming in at third. See, Blizzard Basin. Okay, so we get a map that we need to parse in somehow. We have arrows that are blizzards. So this is a blizzard that moves right. This is a blizzard that moves down. Think they only go up, down, left, right. So there's empty spaces, there's walls, there's blizzards. There are 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. This is a 5 by 5 area. Here's a more complex example. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 6 by 4. So the playing area size changes. And then for our puzzle input, it's big. So each minute, the board changes, right? So we've got an initial state here. We are here in the top left. There's the finish in the top or in the bottom right. And on minute one, let's ignore where we're going for a second. On minute one, all of the blizzards and stuff move in their own directions. They loop around. They can overlap so they don't affect each other. And then the only other issue is the time. So if we think about how we would solve this regularly, if these things weren't moving, then I would probably do Dijkstra's or something like that, or A star or whatever. Shortest path from here to here. Because it's moving, because these are moving in different places, I think we get lucky in that there's a loop. So if we say that there's 6, 1, 2, 3, 4, 5, 6, 6 here, and for height, that means 1, 2, 3, 4, and then we're back here, 2, 3, 4, back here, 2, 3, 4, if we were going down. And then the same way this way. So 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. So we know based on the mod, or basically every 6 turns, 1, 2, 3, 4, 5, 6, back. This one will always be here every 6 turns. And this one will always be here every 4 turns. So if we wait for those to line up, we get there in 24, I think is the first one, right? Technically, they both go into 12 as well. So like 6 and 6 can 12, and 4, 4, 4 is 12. So I think 12 would work too. So what is that, least common multiple? So these should loop at the least common multiple. So if we think about that, then this initial state, this one that we're given here, loops every 12 moves, which means that we can think of these points as points in 3D space, right? So instead of this being, let's call it 1, 1, this can be 1, 1 at time 0. And this is 1, 1 at time 2, 1, 1 at time 3, and so on. So we can keep track of the blizzards for all 12 of those steps. And at that point, we can take all of that information and have built up a graph. So we have a graph of basically 3-dimensional points that you can go to from starting. So you start at 0, 0, 0, right? Or actually, I think this is 1, 0, 0, where we have X, Y, and time. It's like we layered all of these, right? If we stacked all of these minutes, all of these boards on top of each other, there's 18 of them here, right? If we stacked them all vertically, we would have a whole bunch of points that you could potentially go to. You can only move from like the bottom board to the next board. You can't move on your own board. So the only catch then is the rotation back. So on the loop, which is what, 12 or something like that, we need to reconnect it back to the zeros, at which point we have a graph of all of the paths that go through, even if it loops around. At which point I think we can do something like Dijkstra. I don't know what the loop does to us, but we can get started, I think. So let's get started with the test input that we're going to need to use. Throw this into the test input. I think that for every blizzard or whatever, we could do like the position mod, the length plus like 3 or something, or plus the original position. So that would give us the blizzard positions for the cycles. So let's get started with, let's put everything in actually. So wall, blizzard, and space. I'll derive debug because I always forget to do that. We'll parse the field in, input, string slice, I result, string slice. And then I think we want a representation of each of these that is like IVEC2 cell or something like that. Is IVEC2 the right type? So then we get separated Should we do a new way of parsing today? So if we do the parser like this, many1 alt with the iterator that we've been using, then car, but these need to be a blizzard in a specific direction. So I'm going to create a new enum called direction, left, right, up, down. We'll map over each of these, throwing their values away. And this will be cell. I think blizzard is the most common. So this one will be space. There's wall. And then these 4 are all directions. All right, so we've got up. This is supposed to be right. Well, I can change either of them. I'll go left and right like this. So down, up, left, right, dot and hash, terminated in line ending or end of file. So if we iterate over everything with enumerate, we flat map, we into iter enumerate, we get X, Y, and cell. So we have the X, Y positions of every cell, and we can collect that and return it. And if I debug field, cargo watch test, then we get a lot of what we saw last time. So I think that we want to immediately do a display implementation because that's super useful for debugging purposes. The question I have in my head is, do we want to debug every step as well? We can always map over it to do that. So we'll do it on IVEC2. So this is going to be a field that contains the hash map. Then import display for field. Use Rust Analyzer to import display from standard format display. Use Rust Analyzer to implement the missing members. We have to write F with a template string and then our value. So we'll do self.0.iter.sorted by, and this will be, I think it's going to be a tuple, but let's check. Did I not bring in iter tools? Into iter, IVEC2 cell. So we'll collect this into a string. The hash map iter, name these A and B. Oh, right, it needs to be a macro, first of all. And then I'm not sure why sorted by isn't value type string cannot be built from iterator item IVEC2 cell. I know that. I'll just throw in a junk map here to get those strings. Why is sorted having an issue is really the thing that I'm trying to get at. Takes a 2 tuple as an argument. Oh, it takes 2 distinct arguments. Okay, it needs to be A and B. So this will be a.x or a.0.y, a.0.x.comp reference to b.0.y, b.0.x. So this is just organizing all of our IVEC2s with the y value at 0 first and the x value at 0 first, so that we can put everything out into a string. We can match cell here, cell wall is a hash, cell space is a dot, cell blizzard. I think I'll match on each of these, the 4. We'll do left, right, up, down. Then we get left, right, up, and down. We aren't actually using Vex, so I'll put a underscore there. And that should give us a display output. So let's do, where are we? Let's do print line, display formatter without that capital P in it. And then we need to join on new line is what we need to do. So self.whatever.iter.sorted by.map.chunks, which we don't have the number for. So we get the X max as a usize. We do it by going through the hash map, iterating over the hash map, mapping over that, which gives us the keys and the values. We get the X value. We do max on all of the X values after this map. And then we unwrap that because it has to happen. Then we chunks. We get a chunk, collect those chunks into a string, join them with new line, and we should get our new lines. Looks like we are wrong. So it should be what, max size -1. 1, 2, 3, 4, 5, 6. Oh, +1. Minus +1? That's not, that's not it. There we go, +1. And that gives us our full board here, which is great. Okay, so now we have a display for the board so that we can easily check if we did anything wrong. We have the parsed board in that has all of the items, the walls, the empty spaces. I think the starting point is always the same. It's always 0, 1 or 1, 0. Yeah, it's always the same. And the ending is always the same, but we will have to calculate the ending because it's dependent on the length. So we probably want to be able to get the max value of the field inside. So I'm going to impl field here. I'm going to do function get inner dimensions, maybe. That's going to take a reference to self and return an IVEC2, I guess. And I think it's going to be the same thing, right? So this will be X max and Y max. And this will be IVEC2, new XY, both max, b.y. Ooh, actually, you know what would be really interesting to see? If there's any vertical blizzards in either the last or the first ever. Get your puzzle input. There's no vertical in the input for going up or down in the first or last slot. So I think we are permanently good. We can ignore that. We can only deal with the inner field, which is nice. So if we get the inner dimensions, we should get, this is 7 by 5. 1, 2, 3, 4, 5, 6. 6 by 4 is really what we should get because these need to be both -1, right? So it's this -1, that -1 because we're looking for the size of the inner. So this is 6 and 4. So we will only ever have, wait, is that right? 6 and 4 is what we want. But I think the reason it's right is not what I was thinking. 1, 2, 3, 4, 5, 6, 7, 8. So y is the maximum value 0, 1, 2, 3, 4, 5, 6, 7, and then 6. And because it's 0 indexed, then we get the inner size. So a little not what I really meant to do, but 6, 4 is the right answer. And we get that because it's 0 indexed. So we only need to -1 instead of -2. So that's cool. If we go back to process part 1, we get inner dimensions. Field size is this. And then, so we could pull in a crate here, or we could do something really silly. So itertools has this funky thing called k-merge. So if we take field size dot x dot dot, right, infinite sequence from x, and we do field size dot y, infinite sequence from y, and we stick those in an array. We iterate over that and we call k-merge. See, range from I32 is not an iterator. So if we have k-merge of field size dot x infinite and field size dot y infinite, and we do tuple windows, then we can do dot find a b, a equals b, and that's LCM, I think. So if we debug LCM, then we should get 12. It's not the, oh, that's not what we need to do though. We need to do this infinite dot step by field size dot x, right? Step by field size dot y, because otherwise we have an infinite list. Why is step by not working? What does step by take? U sizes? We can do that. We've done that before. So now we have 12 and 12. So what we did here is we took field size dot x, so the width of the inner field for x and y. We turned those into infinite iterators that kept giving us multiples. So we've got x, 2x, 3x, 4x, etc., and y, 2y, 3y, etc. We do into iter there to get the values. We k-merge it, which will sort this for us. So it will keep giving us values and do that kind of like, if we're at 12 and 4 is at 8, then it'll go up again. If we had something like, I don't know, 51 and 2, then it would be 2, 4, 6, 8, 10, 12, etc. And then we would get to 50, it would go 50, 51, 52, 54, 56, etc., skipping those ones until we got to 102, at which point it would be the match. So this k-merge is going to take care of making sure that we iterate in a sorted fashion. We can then tuple windows because we need the next two values. So if any two values next to each other are equal, then we have a match for the LCM. So it's kind of a naive way of doing LCM. You can also do like prime factorization and things like that, but I didn't. So I think 12 is the number of steps that we need to go. So let's do find. We unwrap this because there has to exist, and then we just get 0. So let's call this, I don't know, step cycle number. So we've got the field itself, we've got the field size, we've got the step cycle number. We need to generate the next set of blizzards, basically. So we need a function on field probably. That's just called step. And we take self and we return a field. We could return self. We have to iterate over everything. I feel like we really only need to iterate over the blizzards themselves. So maybe we do self.0.iter.filter, filter map maybe, and then we do, this is a cell, so we match on cell. Of course, this is a position in the cell. Filter map accepts a tuple in our closure. We fill the match arms for cell, wall is none, space is none, and blizzard is some direction. So this gives us the, let's say the position and the direction. So we've got the XY position and the direction of every blizzard. We then want to, I want this to be used so that we don't see that giant yellow warning. So we filter out to get all the blizzards. Once we have all the blizzards, we match on direction to figure out what to do with them. So I think specifically we should just write this out. So if self.get, self.0.get, position plus ivec2, which is what with left -1 0. Just match on this then. And it's either some cell, right? So it could be any number of cells. If it's some cell wall, then we have to do more. If it's some cell, if it's anything else, actually, we don't care what it is. It should never be none. So we'll panic here. Because if it's none, that means we did our inner field calculations wrong and we moved something outside of the wall. We know that the walls are only ever going to be outside. So if it's a movable position, a position that we can get to, something's wrong with plus sign up there. What is wrong with plus? Cannot add ivec2 to a reference to ivec2. That's fine, right? This is an ivec2. That's a reference to an ivec2. We could dereference that. And then, oh, for this whole thing, it needs to be a reference to get the get. So we're basically going to do this match every time. If it's a wall, then we have to flip it to the other side. If it's some, then let's do like new field equals field hash map ivec2 cell. So this is going to be field hash map new. And we're going to fix the type signature over here because this only needs to be field. And this has to be mutable because we're going to push into it right now. So cell blizzard direction, some position direction, right? We get the position and the direction. We match on direction. I feel like this is going to be a for each, not a map. For each position direction, we match on the direction. If it's left, we try to get the position to the left of the blizzard. If it's a wall, then we have a to do. If it's not a wall, if it's a blizzard or a space, then we can move there, which means that new field .0.insert this position. So maybe we should calculate this position first. Desired position equals that. So this is where we want to go. And if it works, that is where we go. And then this is cell blizzard direction, which probably has to be dereferenced. So it's probably a reference to one. That is true. It is a reference. And also move occurs because it doesn't implement copy. We can implement copy for this. It's an empty enum. It's fine. So if we do copy, we need clone. We can only need to do it on direction. So that's this. New field.insert the new position of the blizzard. Otherwise, we have to find the rightmost wall, insert left of rightmost wall. So it's going to be an insert like this, but we find the rightmost wall, which means that self.0.iter.find a ivec and a cell, where cell equals cell wall and ivec.x equals position.x, right? And that always has to work. And I think cells don't have equality on them. So like a cell wall can't be compared to a cell wall right now. So if we do this, then we also need to do it on direction because direction is contained in a cell. So we come back down and let's say wall position equals this dot 0, but left of wall equals wall position plus this ivec that we want to move to. So left of wall, otherwise we insert left of wall here, done. Expected unit found option on 88th. Yes, because this isn't supposed to be returned. Okay, so this works. It's a little bit nested here, but it works. Could also do it, I think, a little bit less nested if we do for a for loop here. So for this, because we're mutating anyway, for position direction in this, and then this mostly goes away. And where is our that? So we get a little bit of horizontal real estate back. Can pull this out to blizzards. So we get the blizzards, we iterate over the blizzards, we match on direction. If it's direction left, we have a desired position. We try to get I think we can reuse this logic. So instead of writing this 4 times, let's take this and let's call this function. What are we going to call this function? I want to put it above step. Let's do function move blizzard, reference to self, mutable reference to another field. And then we stick this in here. Current position is an ivec2. Let's call it position. Position is an ivec2. And then this is the thing that we need to pull out. Movement is going to be an ivec2. So like that. And then direction is something else that we need to pass in, I think, because we need to construct the blizzard. But if we go into left now and we do self dot move blizzard, right? New field position, and then movement is this. Not both of them, just the one of them. It doesn't need to be a return value either. So I'm going to put a semicolon there. It's going to be a reference. And we still have some issues. What desired position equals position plus movement. Ooh, we're not finding the max one here, actually. So find ivec cell equals wall, and ivec.x equals position.x. Direction still needs to get passed in. I'll put it in here. So that all technically works, but we still need to generalize this. I think we could actually do movement in here. But movement equals match direction, right? So this is going to be an ivec to -1, 0. Same kind of issue for the other ones. So based on which direction we're supposed to be moving in, we know. So that's good for us. So let's get rid of movement as an argument. So we don't even need to think about it. We just move Blizzard. And then we also need to handle this. So we find for cell is wall, and let's do let is wall equals this. Let is in row or column equals match direction again, right? So for direction left, we would get ivec is position x, right? Is this right? If we're moving along the x-axis, we defined the walls in the x-axis, and ivec.y is greater than position.y, right? Position is the current position. So this is a Boolean. So is wall and this, right? So we find that, which means that we can just take this and copy it over into a couple places. It's awkward that that pastes 3 lines in 3 different places. I want that to paste. Oh, that's really annoying. I'm sure there's a way to fix that, but I don't know it off the top of my head. So this is less than, these are y's. This is less than because 0 is up. These are x's. These are y's. We'll call this find exterior wall instead. And then I think we're good, right? And then we can just keep calling this move Blizzard, new field, position, and the direction we're moving in which case none of these matter, right? We can just move Blizzard like this. And then the only issue is that for the printout, we don't have the spaces filled in, right? So if we want that nice check, we have to fill the spaces in if we want to be able to print out each board. So ideally we have Blizzards in all positions, right? And we can copy over the walls. So if we have a wall, then new field.insert, new field.0.insert, position and cell, because it's just a copy over. Probably need both of these to be dereferenced. Probably need this to be the same return type for both arms. This is just going to be unit because we're not going to do anything. Cell here looks like it is in need of something. Expected enum cell found reference to cell. Cool. Move occurs because whatever. Doesn't implement copy. We can copy. We don't care. We're not here for extreme performance anyway. So we should have walls and blizzards, at which point if we iterate over all of the interior spaces, right? If we self.get inner dimensions, that gives us 6, 4 for a size that is 8. So if we do +1 for the x's and +1 for the y's, that puts us in, we'll just do +2. We'll go over all of them. Right, and if we debug total size, we should get, is it nothing because we're not running this? Because I didn't call step yet. Where are we stepping? Well, next field equals step field. Print line, this, next field. Step has an issue. Ah, right, because it's field.step, because we made it an associated function. Yay. So now we should be calling it. At 52, we're panicking, which I think is good. Yes, that is good. We just need to set these up. So all those should be set up. We should get some output, 8.6 for total size, which is good for us. I think that's plenty. I'm gonna use one of my favorite shortcuts, 0 dot dot total size dot x for yx in this, then match new field dot get dot 0 dot get dot is sum. So we actually don't need that. If is sum, rather is none. And this is ivec to new xy, which needs to be a reference for get. If it's none, then new field dot insert this vec then. So we'll do pos equals this, pos and cell space. And we return new field. And if I've written the Blizzard correctly, 235 is this to do. So we should have, ooh, you know what the problem is though? Dang. We have to store this as a vec. Every cell in this field has to be a vec from step 2 on. Either that or Blizzard can contain a vec. I think that's what I'll go with. Blizzard can contain a vec. That means that when we step and we look for all the blizzards, we have to flat map this somehow to get more blizzards in more positions. And then we insert, we'll probably use the entry API instead. So it's a bit of a change. The issue here, since I just realized I didn't say it actually, is that we can have multiple blizzards stacked up on the same cell and they can be pointing in different directions. So if you'll count the number of blizzards here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 blizzards here. 3, 6, 9, 10. We lost 9 blizzards. Got too warm. So blizzard direction. I think this becomes a vec of blizzards. But if it's a vec of blizzards, then it's a vec of cells. So I think this is going to be a vec of directions. It can't be copy anymore because now it's got a vec in it. Copy can only be implemented for stuff that is on the stack, if you know what that means. Basically, clone is heavyweight and copy is lightweight, and vecs are heavyweight structures, would be the way that I would describe that. So blizzard is a vec, right? So when we parse it and we create them from the parser, this is where refactoring is really going to help us from. This is interesting too. That's for our display. What do we display if there are multiple blizzards? Probably just a number. Anyway, this is our parser, right? Cell blizzard this. So for each of these, we are going to wrap them in a vec. Glad I figured that out before it became like a problem, you know? I feel like sometimes you get into Advent of Code and it's like, this is a problem, but you won't figure it out until tomorrow. Okay, so for our display formatter for field, we now have vecs here, not individual matches. So I guess we do cell blizzards match blizzards dot length. If it's 1, then we do something. If it's n, then these are all going to have to be strings now. n.to string it. If it's 1, then we will do blizzards match blizzard 0, which is going to be this, comma here, match blizzards. I guess this is directions more than blizzards. Directions. So cell blizzard is not going to happen, and then these are not going to happen, and then these all need to be toString now. And what have I done wrong? Match incompatible types. That's totally expected. String. Done. Format. This is also toString. Okay. And then we have other things to do. When we move Blizzard for a direction, this will be directions. Ready? For 1 in directions. We're going to pass in 1 like this, and it'll be fine. We'll just iterate over all of them. And then here, when we do the inserts, we're going to need to do entries. So it'll be left of wall or insert, cell blizzard direction, but it'll be a vec. And we also need an end modify here. All that, this needs to be immutable. Does that not work for some reason? Method not found in mute cell, vec.push. Is this a cell? I thought it was a vec. It is a cell. Oh, we need to if let sum. There should be nothing here yet unless it's a blizzard. So if let sum, even though we haven't encoded that, cell blizzard directions.push direction equals, we'll call this cell and not vec because that's what it is. And expected struct vec found enum direction. Is that because, yeah, I misspelled cell. So expected struct vec found enum direction. That is on 112. That's not us yet. 100 is where we need this. If we expand this a little bit, expected cell found option. This is just cell blizzard. So if we have a blizzard with some directions in it in that spot, then we push into directions or we insert 1. And then sum is if in the field we get something from the desired position and it is not a wall, then we have to run the same thing, right? Because it could be either. And this is going to be entry on desired position instead, yada, yada. That doesn't need to be mute cell. Let's get rid of that. Cannot move out of cell, which is behind a shared reference at 152. 152 is new field, 0, insert, cell. Instead of dereferencing here, which was what we were doing to copy that value, we are going to clone. It's a heavier weight operation because we have those vecs inside of it now, but hopefully we now have the right output. 1, 2, 3, 4, 5, 6. So right 2 space right. Let's look at minute 2. Right 2 space right 3 space left. Left, left. 2, 2, 2 with a right that is missing. And then right, down, up, left, right, down, up, left that are missing. Not exactly sure where those went. Feel like that blizzard at the top disappeared. So let's start with this bottom one that looks like it's not making it. It's either the bottom one or it's the left one. I have a suspicion it's the ups and the downs that are the issue. So if we are at a wall, right, and our direction is left, and we test to see if the wall is in our row, and we test to see if the y value is greater than our position dot y. Does that make sense? We're going left. If we're going left and any position that is in the old map is equal to the position we're currently in, that doesn't sound right. This logic is wrong. So we're trying to find the exterior wall. If we're moving left and we hit the left wall, we need to find the right wall. So we need a wall that is greater on the x-axis and the y is equal, which means that right is less than on the x-axis and y is equal. Same thing for these. So just a little bit of math gone wrong there. And then if we have a wall position, can we use the movement for all the sides? I think we can. So what do we end up with? We end up with moving all of the walls. Left of wall position movement and modify cell. That's not good. That's even worse. I think this is basically a printout error, but so we find all the walls, right? This is the wall position. So left of the wall is the wall position plus the movement we're trying to take. So if we found the right-hand side wall, then we try to move to the left. We look for the position that is left of the wall in the new field, and we modify it. If it's a blizzard, then we push in the direction. Let's debug cell here. I have a feeling that cell is shared reference to cell. Do we not make it? So we basically are not making it here ever. So that can't even be the problem. Are we trying to push direction in here? Yes, we are. Interesting. Because I think they all hit here. Oh, there we go. Not here. We have some not here's. We do hit some walls. That's good. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So this is all of our blizzards. We are doing 19 blizzards. That's correct. So we could here debug position, desired position, right? So position 6, 4. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4. So this one would want to be 7, 4. That doesn't sound right. Did I mess up? Left is -1, right is 1, right? Direction left needs to go -1. Direction right needs to go 1. Oh, because it's this one, because Y is at the top. I always try to treat Y as the bottom left, and it's always the top left. So this one right here is trying to move into the wall. It's trying to make 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4. It's trying to go right here into the wall. And it gets to what? That's a good question. What does it get to? Wall position. We aren't doing anything yet. We either end modify or we insert. I'm going to go with we are or inserting here. If we debug left of wall, then we're doing an entry on that spot. So that's where it's going no matter what. So if we get 6, 4, it wants to be in 7, 4. It goes to 1, 4. 0, 1. Goes right here. That's where it should go. That's where it's supposed to go. Well, we've got a lot going on here. So let's take a look at what? 0, 1, 2, 3, 4, 5, 1. 5, 1. 5, 1 comes in here at some point. 5, 1 is right here. Wants to go to 5, 0. Absolutely correct. Left of wall is 5, -1. -1 is not the right place to be because these are wrong maybe. Whereas 5, 1, 5, 0, it should go to 5, 4. Okay. This looks better. I'm concerned that we have a little V hanging out here, but this looks better in general. Why do we have a V just hanging out down there? 8, 6. What would that even be? 0, 1, 2, 3, 4, 5, 6. So it would be 0, 6 or 8, 6. So 3, 5. 0, 1, 2, 3, 4, 5. No. So 3, 5 wants to go to 3, 6, ends up at 8, 6. That's wrong. 0, 1, 2, 3, 0, 1, 2, 3, 4, 5? What? Hang on. 3, 5. 3 on the x-axis, 5 on the y-axis. Oh, that's the desired position for 3, 4. Never mind. This is wrong too. That's the total size. That's not anything we need to care about. Let's do total size and let's not Let's not print that out because I just confused myself. The other problem is these all come out in different orders because of the hash map. So what is this position then? It's 0 or it's something on the X. We don't know if it's 0. It's something on the X. 1, 2, 3, 4, 5, 6. So that looks like this, right? Position 3, 4 tries to go to 3, 5, ends up at 3, 6. 3, 6 is the wrong spot for it to be in. 0, 1, 2, 3. 0, 1, 2, 3, 4. This one. So 3, 4 tries to go to 3, 5, ends up at 3, 6, but should be at 3, 1. So the one going down is wrong now. That's because I didn't change it. Why didn't I change it? Okay, this is starting to look better. So let me grab this, do this. That is correct. And then minute 2 would be this. And then I'm basically interested in checking minute 12 and 13 after this. So this is the next one. Oh, actually, this needs to be next field dot step. So this is the 2, 2. Yep. So we're looking good. We're looking good. Let's do for I dot dot or for 0 dot dot step cycle number, or rather for I in it doesn't matter. And we keep doing this over and over. I think we could do field equals field dot step. Do that for the next set of fields. Hopefully this is our loop. Let field redeclares. So I have to do this. We also want to do a print line of the original field, and I want to check the debugs so that they don't show up. Left of wall here, all the debugs don't matter anymore. We don't want to see them. Okay, so when we do this, we print out the field originally. Then I'm going to print out just like an empty line here. So this is our original, and this is 12, which is exactly the same. Yes, that's exactly what we wanted to see. So if we do this, then we get all of the steps. We have all of the positions for all of the blizzards, which means that we can do all of the checks to build up the graph. We do want this to be a directed graph because we only want to move forward in time kind of thing. So do I do step cycle -1 so that we get the one right before it cycles? So this is the one right before it cycles. And then we connect final cycle to first cycle, right? So we probably want let edges equals some vec, empty vec. It's going to be something awkward like a vec of ivec3s, which we haven't pulled in yet, which we need to. So that's coming in from Glam. So every edge is going to be an ivec3 to an ivec3, which is going to be, if you're standing on field 1, you can only go to field 2 for the places that are your neighbors or yourself, right? You can be exactly on yourself too. I think you can only move one position. So we get a 3x3. This is probably where that 2D array would have helped, because if we did a 3x3, we could do windows. So next field is field.step, right? So we've got the first field. We do have to do a calculation for the first edge. It's 1, 0, 0. And then in here, I think we also have to connect every ending edge to end X and Y. And then max int, why not? We'll just say the ending there is max int. So we need to connect every right before end space to end X, end Y, max int, which we also need to calculate. So let's say let end position equals field.0.iter dot, it'll be Y max. So let's filter, I guess we filter map. This will be position and cell, match cell, fill match arms. Match arms go above process part 1 for whatever reason. Rust Analyzer is still doing that. What is the issue over here? This is, yes, I know it needs to return an option. Filter map, position, cell, blizzard is none, cell space is some, position, and cell wall is none, right? So we filter map those, and then we max by AB. Something's wrong with max by, because it's AB, it's not tuple AB. So this is 2 ivec2s. So we need to do yx comp y2x2. Is that right? And then this can be ivec2 x1 y y1 ivec2 x x2 y y2. And this needs to be a reference because it's doing comparison, I believe. And that should be our end position. So the end position is 6, 5 allegedly. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5. That is exactly where it is. Perfect. We found our end position. So maybe actually it doesn't need to be max int. It could just be -1. But end position, field 0, iter, filter max. We get the end position. We need end edge spot. I don't know. Cell equals end position dot x and position dot y I32 max int. So this is end edge cell. Edges is going to have to be mutable. So for I in this cycle, every time we do this, we need to find all the spaces that have moves in the next. So what spaces equals field dot zero. We'll call this origin spaces, right? Field dot zero dot iter dot filter probably, right? And this will be a filter map because these will all be spaces. So it'll be position cell, match cell, fill match arms. Cell shouldn't be an option, right? That doesn't sound right. I feel like something else is wrong with filter map. Expected closure that takes us. I got this wrong twice. I got this wrong twice today. Really struggling with the Rust Analyzer right now, or over the last couple of days. I don't know why it's been like that. So if we match cell, we want the spaces only, right? So for origin position in origin spaces, we do some stuff. So for origin position in origin spaces, we need to go for 0.012, so 0.3, Cartesian product 0.3. So we need to get all of these offset from that space. Origin position, I guess that doesn't really work. How does that not work for us? We say that we are 0 to 3 and 0 to 3. That gives us everything from 0, 0 to 3, 3. But we kind of want this to be from -1 to 1, -1, 0, 1, right? And that's fine. Cool. So we map over this. We get the tuple. We have to get all of these positions from next field. We need to get next field, x, y. This will be filter map. Get any of them that are spaces. If let cell space equals this. I guess it's going to be some cell space, right? Theoretically, it could be null, or theoretically, it could be none. This is this IVEC2, though, plus origin position. Next position equals that. Then we also need to get on it. This needs to be dereferenced to be able to add. This needs to be referenced to be able to get. If let sum this, else none, sum next position. Okay, so this gives us all the possible next positions. For pos and possible next positions. Then we do edges dot push IVEC3 new. For these two, it's going to be origin position dot x dot y, and this is going to be I, right? And this is going to be a tuple, and it's going to be another IVEC3, which is going to be new, which is going to be the next, or I guess in this case it's pos. So my question is, one of these is either I or negative I, right? So for every cycle, we take the current field and we connect the current field, which is field 0, technically, I guess, and we add it to I plus 1. So that gives us field 0 edges, or field 0 positions that are spaces that connect to field 1 spaces. So anywhere you can move from field 1 to field 2, or field 0 from field 1 in this case, which gets us to, where's that cell thing that we did earlier? Not the end edge cell, but the cycle, step cycle number. Our step cycle number is this. We only go to -1. So this will add to equal cell cycle number at some point. So here we need to do match cell cycle number. Well, we can do if cell cycle number equals I plus 1, then 0, else I plus 1, right? If it's the last cycle, then we connect it to 0. Otherwise, we connect it to 1. And then, then we still need to do some special cases. We need to do the origin first and the ending last, or the ending repeatedly, actually. So edges should really start off with 0, 0, 0, or like 1, 0, 0. And because this is going to be our starting point. And IVEC3 new 1, 1, 1, 1, 1. So we always connect the starting point to 1, 1, 1, basically the next step. So this position on the second round is always down 1. It's always open, which makes me question the actual input that we're going to actually have to do, which looks like that's true as well. So this will always connect to this dot on 1, 1, 1. And then we're going to assume the same for the end edge cell. So we need to do the same for the end. for every iteration. So I think that we do this for 0 each time, or for I each time, basically. So I'm going to take the easy way out and do possible next positions, right? Or rather, I guess that's origin spaces, right? If we start at the spot above the end spot here, then we can always make it to the end spot in the next one. So this is origin spaces. Let's do origin spaces dot clone dot find, what is this, position? It's an IVEC2. So we could do IVEC2 new end edge cell X has to be the same. End edge cell Y has to be -1 or -1 anyway. If let sum position equals this, then we edges.push the IVEC3 to the end edge cell. IVEC3 needs to be position.x, position.y, and I. This needs to be a reference to be able to compare, or I thought it did. Maybe it is a double reference because we're finding end edge cell needs to be a value, so we can dereference both of these. Are we gonna have, we're gonna have a slightly different issue for end edge cell, aren't we? End edge cell is a tuple. So it doesn't have dot these things. That's unfortunate. Why did I make it that? That's not what I want. That's not what I'm gonna do. That's gonna be an IVEC3 because I want to be able to do X, Y, and Z. So edges push, IVEC3, end edge cell. So we do this, and then we would have the edges, right? Construct graph. Day 21 was our last pet graph. Let's take a look. What kind of graph do we want? I think we want a directional graph, so I think we're good here. This is really what we want. Is this wrong? Do we not actually use pet graph here? We definitely do. Where's the from edges? There's from edges. So here's our edges. Here's the dot code to write out a file. Let's copy that, and then I'm gonna swap these back and do this here. We're gonna import this, or we're not, because we don't have, I got rid of pet graph. So let's do pet graph as a dependency. We test, we import. These are IVEC3s. Doesn't satisfy IVEC3 node trait, and the function or associated item from edges exists for this, but it's not satisfied. If we look at what node trait is, it says a trait group for graph maps node identifier, which is not helpful, but it does need to be ORed here. So whatever n is, which I think is like U32s and stuff like that for the graph map. Impl node trait for n, where n is copy, ORed, and hash, but IVEC3s are not ORed. Tuples are. So it's unfortunate, but because I chose to use GLAM, I don't think there's any feature that will let us turn this on. So if we look at the features for GLAM, there's default, standard, libm, CUDA. If you're not familiar with how I got there, there's a little flag button up here at the top of the GLAM docs, at the top of every Crates docs actually. And it just lists all the feature flags that you can turn on. So I'm gonna go look through them. Any that say this feature flag does not enable additional features means that it's probably enabled by default. So I think these are all on already. It's interesting that the IVEC3s have comparison functions, but it doesn't have an ORed implementation. I guess that makes sense because there's a lot of different ways to compare, but it does mean that for digraph map, these edges are going to have to be tuples and not IVEC3s, which is more awkward than I wanted it to be, but is totally fine, right? So it'll be like this, and then all we do is get rid of the IVEC news because all of these will be tuples, and then end edge is going to be a tuple as well, which means that this is going to be 0, this is going to be 1, and then from edges should work. We need to now re-specify this to be an I32, 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 and we've got our graph. And let me uncomment this. This is going to be a lot of output, so hopefully for the example it works. So I imported everything right there except for the trait for write all, which I always forget. We have graph dot dot there, and our tests are probably freaking out. So if we get this and we go to our friend over here, editor, we end up with an interesting set of just like, this is sitting over here. We should take a look at those and just identify them. And then think what we end up with here is basically all of the gaps in our 0, all the gaps in our 1, all the gaps in our 2. Let's see if that's accurate, right? 1, 2, 3, 4, 5. There's only 5? 1, 2, 3, 4, 5, 6. So what is the extra one? 100 is the starting. Oh, the starting one is the extra one. Yeah. That makes sense. Oh, the way we've written this as well is including those spots every time. So maybe I didn't need to write 100 here manually, but that's semi-accurate. So 1, 2, 3, 4, 5, 6, 7. There should be 7 then, if that's the case. So the edge 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 5 is going to be this edge over here. That's going to be it. 6, 5, 0, right? Because it's not connected to anything. 6, 5, 1, 6, 5, 2, 6, 5, 3, 6, 5, 4, 6, 5, 5, 6, 5, 6. Dang, is it really never connected to anything? That doesn't make sense. That's not good. In minute 2, it should be connected here, right? Minute 2. So minute 2 for us is, this is initial. So initial is 0. This is 1. This is 2. So 2 to 3 should have a 6, 5. And if it doesn't, then I've done something wrong. So minute 2 doesn't have a 6, 5 according to our graph here. It's interesting. I wonder if it's always cut off like this and that's why it doesn't show up. But the 11s never wrap around either. So like 1, 1, 11, right? So 1, 1 right here should have a connection back to 0, 1, 0 or 1, 0, 0, but it does not, which is also interesting. So I think there's 2 issues that I see here. One is that our 6, 5 is always off by itself. Our maxent doesn't show up, but it should be connected to these 6, 5s. So let's see what the problem is there. I think I don't need this, so I'm going to verify that. 1, 0, 0 and 1, 1, 1. Let's run this. Let's have it write the graph dot out. Oh, it's super interesting. It changes every time too because the order of the hash map changes, I think. So if we paste this in here, then we get 1, 0, 0 still connected to 1, 1, 1. 1, 1, 1 doesn't have a way to get out. So it needs to insert itself. It needs to be able to go to 1, 1, 1 in the next one. That's one of the ones that we're missing. For every single edge, it needs to be able to stay in the same edge every single time, unless a blizzard comes out. So for edges, we've got origin position in spaces. And right here, we can start off immediately with a check, right? I guess we're already checking that position though. So 1, 1, 1. So this is 1, 0, 0, right? And 1, 1, 1 exists there. And it should also connect to 1, 1 or 1, 2, 1. Where's 1, 2, 1? 1, 2, 1 is right here. 1, 2, 2 is right here. These are connected to 1, 1, 2. Why are these connected to 1, 1, 2? Because 1, 1, 1 can't get to 1, 1, 2, but it should be able to. Like that should be an option at least. There's 1, 1, 3. But all of them going down from 1 to 2 to 3 to 4 to 5 for the Z index is correct. But I thought we were checking them here. So possible next positions, -1 equals 1. Next position is x, y plus origin. So this would be, for example, 0, 0 plus 1, 1. If the next field is a space, then we return it. So if we're at 1, 1, 1 and we get 0, 0, let's print out all the 1, 1, 1s. The other thing is, for position and possible next positions, we push the origin to that next position. Yeah, let's do if origin position equals IVEC 2 new 1, 1, right? That's the position we're interested in. Interesting. Interesting being that we get origin positions, but we never get 1, 1. 1, 0. 1, 2. Oh, this actually should be much higher. Let's do debug origin position here so that we don't debug so much stuff. So origin position 1, 2, 1, 0. This should be a print line because it'll be easier to read, even if we use the debug formatter. Got all these IVECs. 1, 1 never comes up in the origin positions, which feels really weird because it should. Oh, no. I know what I did. Oh, that's really unfortunate. Okay, so field equals next field. I wasn't resetting the field basically. So my guess is that, yeah, there we go. There's our debugs. So it was just the first setup basically over and over. So let's pull the new graph dot. And now we get something interesting. Now we get, here's our last position over here. And it's like, this can go there, this can go there, this can go there, etc. And then the other thing that's interesting is that the 11s never get to 0, which is something that does need to happen. Or rather, I don't know that it does need to happen, but we have this and this never gets hit effectively because this is 12. So if we got a step cycle number there, we never see it pop up, we were going to have to do an additional iteration anyway. So I think maybe just not doing this -1 and doing that if expression was the right move in the first place. So if we do that here, we hit the step cycle number now. If we look at the graph dot should have 11s that point back to zeros now, which is going to make this look a lot different. This is our graph now, right? This is absolutely very different, right? So a time z goes to a time 4 to a time 5 to a time 6 to a time 7 to time 8 to time 9. So you see how we have everything theoretically connected, but connected in a way that the graph is set up. Where's 0? The graph is set up to only be able to go through this 3-dimensional time. I know there are other graph dot layouts, but I don't know that it's even worth trying to use different layout algorithms. Right, label 111, for example, is somewhere. Where? I don't know. It's interesting that there are these positions like 631 that you can never get to because they can only go somewhere. Those are 6s. These are 4s. 148. Oh, I was looking at them before. There we go. 114, 105, 106. So 100 right here. That's our starting point. And 1011 is the only one that goes back to it. So that's interesting. So now that we have everything set up, hopefully correctly, let's minimize that and the fewer number of minutes required to avoid the blizzards and reach the goal is interesting. So I will say that every move is a minute. So here's our algorithm because I can't spell the person's name. I'm going to do here so that we don't see all that red. I'm going to import the shortest path algorithm. The starting point is going to be 100 and the ending point is going to be some, what did I call this? The end edge something or other. I gave it a horrible name. End edge cell. I don't know what I should have called that, but maybe not that. So if we do that, then the result gives us all of these. It looks like 10. What is the actual answer for this? Does it tell us? 18 steps. So we only get up to like 11. Interesting. There's a bunch of endings. Is it endings because of the loop? Big question is, should we be using a different algorithm? Shortest path algorithm, length of shortest path from start to every reachable node. Graph should be visitable and implement into edges. Edge cost should return the cost for a particular edge, which is used to compute path costs. Edge cost must be non-negative. If the goal is not num, then the algorithm terminates once the goal node's cost is calculated. So my first thought is that we set up the end wrong. So end edge cell, right, is this fantastical cell that can only be reached from 6-5, right, in this example. Is that correct? 6-5 is constantly in. So if we don't do this and we pass in none, then what do we get out of this? We get numbers up to the 18s. 651, for example, but that's still wrong. 650 takes 12, which is presumably theoretically impossible. 656 takes 18. That's the right answer. Let's see, if end dot 0 equals 6 and end dot 1 equals 5, then let's make this the end edge too. So the end positions, that wasn't the correct thing for that. What happened here? No implementation for I32, I32, I32. Ah, yes, because it's n.0.0 and n.0.1, and thus these don't need to be borrowed because they're already. Okay, for using end position, because end position is actually finding, right? Finding from field. So max by unwrap, we would have to do what we're doing right now, do something like this and clone that so that it's no longer like that. So is there any way to rule more things out of this? Because we've got 6-5 in so many places, right? And 656 is the correct answer, but that doesn't sound right unless it loops around again. I mean, which it has to for all of them, right? So the question for me is, we have all these 3-dimensional points. We have an answer. Let me take a look at this, paste it in here. It looks basically the same as we had. So if we start at 100 here, we've got two choices that don't really matter into one choice. So 1, 2, 3, 4, 5. And then it looks like 215 can only go to, that's not just a random line passing through it, is it? 215 can go to 126. Is that true? 215. Oh no, I'm doing diagonals, aren't I? Why did I do 3 by 3? This isn't a diagonal. Like, you can't move diagonally, can you? Why did I do that? Right? We've got -1 and -1, but it's not every position. These diagonals get through. And they shouldn't. Dang. Okay, so this will be a little bit easier though. This will be y's and x's, right? So -1, 1 is not a position. So it's either -1, 0, 0, 0, 1, 0. Those are all the y values, or 0, -1, 0, 1, and then iter that, or into iter that, because it matches what we were doing before and it doesn't matter. So we get up, down, left, right, and the one that we are on. So we can wait, or we can go up, down, left, right. Why did I? And now the minimum value is 18 here. So that's the answer. So it's result.iter.map and value. And we can get rid of a bunch of this. We map over that. If those are credible positions, then we return value. So this is a filter map. So this will give us, why is that looking weird? I32 is a primitive, therefore doesn't have fields. N.0? Right, because we're filter mapping over. No, because I destructured it. That's why. So it's .0 and .1, filter map, min, unwrap to string, and 18 was the move set. Okay, so we are passing part 1. This is easily the longest I've taken to do any of the days, even though it didn't feel particularly like the hardest day so far. Well, yeah, day 16 felt like the hardest. This felt, I wrote a bunch of code, maybe too much code. I don't know. I'll judge it later. But I did have a solution that I thought was going to work. Or rather, I had a solution that I knew would produce a right answer. This is not writing out that dot file anymore, is it? I want that dot file. I like that dot file. Yeah, I want to look at what this actually looks like. There we go. Significantly smaller graph. Okay, so let's get our puzzle input, make sure that we put it into our input here, paste it in, cargo run bin part 1, watch the logs that I put out for some reason. Ooh, right. We don't need to write this dot file out anymore. I left debugs in here and it's not the best. Let's get rid of field, get rid of this. 260 it says. So it took a second to run. I hope this is the right answer, because if it's not the right answer, then, oh, it is the right answer. That feels so good. As the expedition reaches the far side of the valley, one of the elves looks especially dismayed. He forgot his snacks at the entrance to the valley. Since you're so good at dodging blizzards, the elves humbly request that you go back for his snacks. From the same initial conditions, how quickly can you make it from the start to the goal, then back to the start, then back to the goal? In the above example, the first trip to the goal takes 18 minutes, the trip back to the start takes 23 minutes, and the trip back to the goal again takes 13 minutes for a total time of 54 minutes. So we need to retain the state of the field to do part 2. Actually, we don't. We've done this in a way that it works for us. We just need to find a way to reiterate again over it multiple times. So this is our result, right? This is our, I'm going to copy all this into part 2. And we are going to say these. I think we have the full graph. We just need to know which of these is the one to do. So this is from our starting position everywhere, so that we find the end here. This filter map now has the value we're looking for. So let's filter instead. And let's say, is there a min by? I hope there's a min by. This is end, this is whatever end value. So is min by a function? So if we min by key, then we get this and we return value. Does that work? Min is that option. It needs to work. So let's debug min. What is the test case answer? 54, but it's 18, 23, 13. So I'm going to move this ignore up to part 1, save, test. So we've got 18 for 6, 5, 6. This is our starting node now. So we have to do the same thing. To goal, and let's do back to camp to goal .1 or .0, I guess. And back to camp means we are looking for start position, which is 1 and 0. And we debug back to camp 1823. And then we have back to goal, and this is back to camp dot 0, and we debug back to goal. And that's 13. And we do goal dot 1 plus back to camp dot 1 plus back to goal dot 1 dot 2 string. And that is not good because I've put commas in it for no reason. Okay, so that is a passing part 2. So let's build in release mode for part 2 and run it. 747, allegedly. That is correct. So day 24 took us a while, or at least it took me a while. But we built up a solution that works. It works flexibly enough to solve part 2 inside of like, I don't know, 10 minutes or something like that. So overall, I'm happy with this. So let's take a look at what we're doing. We're parsing the field. The field is of type field. So that is a hash map of IVEC2s in cell. We define an associated function on field called getInnerDimensions that gives us the dimensions of the inside of the field, the playing area, minus the start and the end position. We calculate the least common multiple of the X width and the Y height for the field. We do this by using itertools. So we do an infinite iteration stepped by the X width and an infinite iteration stepped by the Y width, Y height. We use K-merge to combine those two iterators sorted ascending. So because we've done that, we can tuple windows and we can just find the two numbers that are the same in a row. And that means that we've found the lowest common multiple of the X and the Y. This matters because each of the blizzards only moves in one direction. It's either up and down or left and right, which means that their cycle time is equal to the width of the field or the height of the field. So we need to find the cycle time for when all blizzards match back up at where they were when we started. And that's how we do that. We then calculate the end position. This is just programmatic. It ends up with being the bottom right empty space, basically. We do that by iterating over the field. We filter for only the spaces. We do a max by these tuples. These tuples will sort in a place that gives us the bottom right tuple, the Y max with the X max. Then we set up our graph. Our graph is a 3 tuple to a 3 tuple. So remember, we've stacked all the fields in a 3-dimensional space. So we've got X, Y on each of the fields, and T time is our third variable here. So if we are on field 0, field 1, field 2, field 3, that's the Z value. You can only move from the previous field. So if you're on field 0, you can only move to field 1. If you're on field 1, you can only move to field 2. So that helps us set up a directed graph. We set up a directed graph. We create all of these edges by using this step function on field, which returns us the next field. So it iterates all of the blizzards to their next step. We've calculated how many steps we need to do to cycle. So that's what this number is. It's iterating exactly the least amount of times we need to cycle a full blizzard set. So step is one blizzard. It just moves them all forward. We then get all the spaces in the original field, all the empty areas that somebody could move to theoretically, or somebody could be standing in more accurately. Then for each of the positions that we could be standing in, we check up, down, left, right, and the spot that we're standing on, because we could choose to not move. And we look for those in the next field. If those spaces, or if any of the spaces we're looking for that we can move to are available for us to move to, then we keep them around and we create edges from the position that we were just in to the position that we will be in. And we use the Z index as time or step or field number, whichever thing you want to call it that makes sense. The only difference is that when we get to the end of the cycle, we have to re-loop the graph, because the whole point is that we created this cycle in this graph. So, or it's not technically a cycle. We haven't checked to see if it's a cycle, but it is a loop back. So it loops back on the spaces in the first field from the, I want to say 12th field, the last field, whatever that is. So if we are at the last iteration and adding 1 to I to calculate the next field's stuff, spaces and things, puts us at that loop point, then we point our Z index to 0 instead of that max number. And then we set field equal to next field, which is really important. And I lost about half an hour debugging just this one line. We use a digraph map with nodes of type tuple, 3 tuple of I32. We just constructed the edges, so we get the graph for free. We used dot to log out a representation to look at and help debug. That was really useful. And then we use Dijkstra to find the shortest path from wherever we start to everywhere. The edge cost is all 1. We start at 1, 0, 0. In this case, part 1, all we need to do is find the minimum value. So for every end coordinate, there is an end coordinate at every time. So there's a 6, 5, which is the end coordinate at time 0, at time 1, at time 2, at time 3. So what we're going to get here is probably a list of like 12 results. So we need to find the minimum one from all of those. For part 2, it's the same thing, except when we do find the place that we got to, then we use that as the starting place to get back to the starting position. And then we use the original position to get back to that. And then we have to add up the travel time to get there, back, and there again. And that's it. So I actually had a ton of fun on this one. I really like using PetGraph always. I love using PetGraph. It's so much fun. So I hope you enjoyed this one. This is going to be one of the longer ones alongside the last couple of days. So if you're still sticking with me, I really appreciate you. If you've watched all the videos, throw a like on the videos. It helps out. And I will see you tomorrow, either for day 25 or for whatever they throw at us. I hope you have a great rest of your day.